Hello, this is the section 4.10 lesson. In this section we're going to discuss a simple technique for determining if a population is normally distributed using sample data. This topic is generically called assessing normality. So to illustrate the need for assessing normality, let's look at this example. Given below are the average daily temperatures in the month of November for the city of Lincoln, Nebraska for 9 different years. And so here our first data value is 32.6. So that means that in one particular year, the average temperature in the month of November was 32.6 degrees Fahrenheit. In another year, the average temperature was 33.1. In another year, the average temperature in November was 36 degrees, and so on and so forth. And so we might want to use this data to calculate a confidence interval estimate of mu, the population mean temperature. So out of all years, we would like to calculate a confidence interval estimate of the mean average high temperature in the month of November. So this looks like a fairly simple problem that we could solve using a t-interval. Remember, a t-interval was a confidence interval estimate of a population mean. But if we remember the requirements for that t-interval, there were two. Number one, the sample is random. Well, that's met in this scenario because we said that the data was randomly collected. But the second requirement is that we need the population to be normally distributed, or the sample size needs to be bigger than 30. Well, in this case, our sample size is only 9, so this part is not met. So that means we need to meet the first part of this requirement in order to meet the overall second requirement. So to meet the second requirement, we need to determine if the population is normally distributed. If the population is normally distributed, then we've met this second requirement, and so we can calculate a valid t-interval. But if the population is not normally distributed, then that means we need a bigger sample size in order to meet this second requirement. So one way to determine if our population is normally distributed is to form a histogram of our data. And so here's a simple histogram of these 9 data values, and I used 4 bins or 4 intervals here. And so remember that in a histogram, a bell curve shape indicates a normal distribution. Well, in this case, we look at this and we say, well, it does kind of have a bell curve shape. It starts low, increases to max, decreases to a low again. But on the other hand, we might argue that, well, it's not symmetric. The left half here is not a mirror image of the right half. And it looks like maybe our data is skewed a little bit to the right. And so we might be tempted to say, well, maybe the population is normally distributed, or maybe it's not quite sure. And really the issue here is that we've got a real small sample size, and so a histogram is going to be a little bit inconclusive. What we want is a little more objective way to determining if our population is normally distributed. More objective than simply looking at the shape of a histogram and determining if that's a bell curve shape or not. And so the technique that we're going to talk about here is to form a statistical graph called a normal quantile plot. And so let's talk about the algorithm here for constructing a quantile plot. Now, different statistical software packages use different algorithms for generating quantile plots. The one we've listed here is rather simple, but in the end, the interpretation of them is all the same. We'll talk about that interpretation here in a minute, but let's talk about the algorithm first. So the first step is to arrange the data values in increasing order. So that means x1 is the smallest, x2 is the next largest, x sub n is the largest. Second step is for each data value, the first, second, up to the nth, define this quantity p sub k equals k divided by n minus 1. So we take that subscript k, divide it by the sample size plus 1. And then the third step is we calculate z sub k, which is defined to be phi inverse of p sub k, where phi is the standard normal CDF. And so let's illustrate how this is done with our data. So here's our data value that we've arranged from smallest to largest. And then the next step, we calculate P sub k. So to calculate this value, we take k, which is 1, divided by n plus 1. N is 9, so 1 divided by 10. This number is 2 divided by 10, 3 divided by 10, so on and so forth. Now here to calculate z sub k, what we're going to do is go to table C3 in the appendix, and which is our z-score table, and we're going to look through the center of the table for an area as close to 0.1 as possible. And then the corresponding z-score is the value of z sub k. So we look for an area as close to 0.1 as we can find, and the corresponding z-score is negative 1.28. To find this z-score, we look for an area as close to 0.2 as possible. The corresponding z-score is negative 0.84, and so on and so forth. So now after we've calculated those values, we form our graph by plotting the points x sub k, comma z sub k. So what that means is that on our horizontal axis, we're going to plot those x values. On the vertical axis, we'll plot the corresponding z values. And then the last step is to interpret the quantile plot. If the points form a straight line pattern, then we conclude that the population appears to be normally distributed. If the points do not form a straight line or exhibit some other type of nonlinear pattern, then conclude that the population is not normal. So the interpretation is to simply look for a straight line pattern. If we see a straight line pattern, then that indicates a normally distributed population. If we see something other than a straight line pattern, then we conclude that the population is not normal. So let's look at the graph of our z and x scores here. And so here's our data that we calculated, and then here's the plot. So we put the x values again on the horizontal axis, the z scores on the vertical axis. It's like this point right here is the point 32.6 comma negative 1.28. This point down here is the point 33.1 and then negative 0.84, and so on and so forth. And so now to interpret this, we look for a straight line pattern. And we see that, well, these dots do kind of form a straight line. Not a perfect straight line, but it is kind of a straight line. And there's no other type of pattern indicated there. And so our conclusion is that the dots form roughly a straight line, and so the population appears to be normally distributed. This doesn't prove that the population is normally distributed, but based off of this graph, it at least appears to be reasonable to assume that the population is normally distributed. So that means that we have met the second requirement for the t-interval, and so we could use our data to calculate a valid t-interval.
Lastly, let's talk about how we can construct a normal quantile plot on a calculator. Now, the calculator uses a slightly different algorithm than the one we gave in this lesson, but the basic idea is the same. So first thing on the calculator, we need to enter our data. So go to the Stat, Edit menu, and then enter your data in a list. Next, we need to go to the Stat Plot menu, so go second, y equals, and then choose one of the statistical plots to set up. Here we'll choose plot 1. Press enter. Make sure that plot is turned on, and we want to choose this last type of statistical plot. Next, we need to choose the name of the list that contains the data. The default should be L1. If not, you can change it to whatever you need. Next, we need to select where we want to plot our data on the graph, either on the x-axis, the horizontal axis, or the y-axis, the vertical axis. We'll choose the default x. And then lastly, you need to choose what type of mark you want to put on the graph. Okay. Now the last step is to go to the Zoom menu and choose option 9, Zoom Stat. Don't forget to choose Zoom Stat. That's the step I always forget myself. And you should get a window that looks like this. This is the calculator's normal quantile plot. Notice that looks very, very similar to what we calculated by hand. However, it's not identical. If we press the trace button, we can see the coordinates of the points that it has plotted. So we go to this first one here. We see the x value. Well, that's our very first x value in our data. The corresponding y value is approximately equal to our z-score. Not identical, but very similar. And if you scroll to the right, you can see the coordinates of the other points, and you'll notice that the x values are all the same as our data, but the y values are very close to the corresponding z-scores. So again, the calculator does not use the exact same algorithm, but the graph that it gives looks very similar to what we get by hand. And the interpretation of the calculator's graph is the same as our graph. We look for a straight line pattern. If we see that, that indicates that we have a normal distribution.